Welcome to our Quantum Deep Dive.
Hey everyone! So today we are going to get into a really fundamental law of the universe, and you won't believe it, but it's the key to the future of our most powerful computers. Now, this whole deep dive is based on a really fantastic essay by Jörg Oesch-Schnippat.
Okay, so let's start with a really big question, a puzzle that's right at the heart of all this next-gen tech. You've probably seen those pictures, right? The ones of quantum computers, they look like these incredible golden chandeliers. But have you ever wondered why they have to be kept at temperatures that literally make deep space seem warm and cozy?
Well, the reason we go to all this trouble, these insane lengths, is because the payoff, it's just immense. You see, quantum computers aren't just like a faster laptop. They're a whole new ballgame, operating on completely different rules of physics. We're talking about solving problems that we currently think are impossible. Designing new life-saving drugs one molecule at a time, or creating communication networks that are actually unhackable. But, and it's a big but, for all that incredible power, they have one critical, glaring weakness.
Yeah, that weakness, it's their incredible fragility. The very things that make them so powerful, those quantum states, the famous qubits, are just unbelievably sensitive. Think about it. The tiniest little vibration, a stray magnetic field, even a little bit of heat can introduce what we call noise. And that noise just completely messes up the delicate quantum dance of superposition and entanglement, wiping out a calculation in an instant. It's a process called decoherence. So the big question becomes, how in the world do you protect something so fragile from our noisy, warm reality? Okay, so you'd think the solution would be some brand new, super advanced 21st century gadget, right? Well, believe it or not, it's not. The answer is actually a deep, fundamental principle of physics, one that was figured out long, long before anyone was even thinking about something like a quantum computer. We have to wind the clock all the way back to the early 1900s. I mean, what an explosive time for physics. It was just 1 year after Einstein completely rewrote the rules for space and time, and this physico-chemist, a guy named Walther Nernst, comes along with this totally radical new idea about the ultimate limits of cold. And this idea, well, it became known as Nernst's Heat Theorem, and eventually the third law of thermodynamics. Now, it makes a really bold claim about this thing called entropy. You've probably heard of entropy, right? In simpler terms, it's just a measure of disorder, or randomness. What the law says is that as you get a system closer and closer to absolute zero, the coldest anything can possibly get, all that disorder just vanishes. So what Nernst is really getting at here is this. Imagine you have a perfect crystal. If you could cool it all the way down to absolute zero, all that random jiggling and bouncing around of its atoms would just stop. Everything would settle into one single, perfectly ordered state, the lowest energy state possible. You'd basically be left with perfect, absolute order. Okay, right. But that all sounds like it belongs in the world of steam engines and chemical reactions. I mean, that's what Nernst was studying back then. So what does the messiness of atoms have to do with, the information in a supercomputer, the qubits? How does this old-school law connect to the absolute cutting edge of the quantum world?
And this is the magic link. This is the whole thing. In the world of quantum mechanics, entropy gets a major upgrade. What classical physics just calls physical disorder, quantum physics sees as information uncertainty, or, to put it another way, noise. So a hot, messy system with tons of entropy, it's also full of thermal noise. But a cold, perfectly ordered system with zero entropy, that's pristine, it's quiet. And that is the perfect environment for a super fragile qubit.
So when you cool a quantum system down towards absolute zero, what you're really doing is forcing it into its lowest possible energy state. Physicists have a name for this. It's called the ground state. And in that ground state, you have the least amount of thermal energy, the least disorder, and, you guessed it, the least uncertainty or noise. The system basically becomes this silent, stable, pristine canvas, just waiting for you to perform a quantum calculation without the world immediately rushing in to mess it up.
And what's really cool is that the math backs this all up perfectly. There's actually a quantum version of entropy. It's called von Neumann entropy. And the equations show, without a doubt, that for a system in that ideal ground state at absolute zero, the entropy is exactly zero. Perfect order really does mean zero uncertainty.
So here's the big takeaway. Nernst's old law basically handed us the recipe for protecting a quantum computer. Cold equals quiet. And if you want to make a quantum computer work, you have to get rid of that thermal noise. You literally have to create the quietest place in the entire universe. Which of course leads to the next obvious question, how on earth do you actually do that?
Well, it takes these absolutely incredible machines called dilution refrigerators. And yeah, those are the amazing golden chandeliers you always see in the photos. It's a whole process, right? It's multi-stage. It starts with some pretty standard cooling techniques, but the real magic, the secret sauce, is this crazy cycle that circulates a special mixture of helium isotopes. And that process actively pumps heat out of the very core of the system, pushing it closer and closer and closer to absolute zero. The temperature they're aiming for is around 10 millikelvin. Let that sink in. That is 10 thousandths of a single degree above absolute zero. To give you some perspective, the background temperature of deep space, the empty void between galaxies, that's about 2.7 Kelvin. This is over 270 times colder than that. It is just an almost unimaginably cold state of matter. And there's a really good reason for that specific temperature. It all comes down to a simple energy comparison. So take a look at this chart with me. That tall bar, that's the amount of energy it takes to flip a qubit from a 0 to a 1. It's a specific amount, and you need to control it precisely. Now, look at that tiny little bar next to it. That's the amount of thermal energy that's just kind of bouncing around at 10 millikelvin. See how small it is? It's tiny. This means it's super unlikely that a random bit of heat will have enough juice to accidentally flip the qubit and cause an error. The cold keeps the calculations safe.
So there we have it. We can use Nernst's law to get unbelievably close to absolute zero, creating this perfect, quiet little pocket of the universe for our qubits to do their work. But, and you knew there was a but, right? The third law has one last twist, a final, fascinating, and kind of frustrating limit.
You can never actually get there. It is physically impossible to reach absolute zero. You see, the law isn't just about what happens at absolute zero. It's about the journey to absolute zero. With every step you take to cool something down, you remove less and less heat. It's like trying to walk to a wall by always covering half the remaining distance. You get from 1 Kelvin to a half Kelvin, which is tough. Getting from a half to a quarter is even harder. You can get infinitely closer and closer, but you need an infinite number of steps to actually touch that 0 Kelvin finish line. And I have to stress this is not a technology problem. It's not like we just need better refrigerators. It's a fundamental, unbreakable rule of the universe. And this impossibility has some really deep implications. For instance, it connects to other big ideas, like Landauer's principle. This basically says it always costs some energy to erase information, and that cost is tied to temperature. So since you can never get the temperature all the way to zero, you can never erase a bit of information for free. And that means perfectly efficient, completely lossless computation, it's physically impossible. So let's just step back and put this all together. It's pretty amazing, right? A law thought up over 100 years ago by Walther Nernst, a guy trying to figure out chemical reactions, turns out to be the absolute bedrock of our most futuristic technology. The third law explains why quantum computers have to be so mind-bogglingly cold. It gives us the roadmap for how to get them there, and it even draws the line in the sand for what they can and can't ever achieve.
And that leaves us with one final kind of mind-bending thought to chew on. The third law tells us that perfect, zero disorder, zero entropy order is just not possible in our universe. So, if perfect order is physically unattainable, what does that say about the ultimate limits of computation? And maybe, just maybe, what does it say about the ultimate limits of knowledge itself? We really hope this explainer has helped shed some light on the, cold, hard facts of quantum computing. And a huge special thanks again to Jörg Owe Schneepat. His essay really was the foundation for this whole deep dive.
If you want to learn more, definitely check out his website. It's schneepat.de. Thanks so much for joining us.
Schneepat.de is a private project by Jörg Owe Schneepat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.